All right, hello. My name is Christian. I'm presenting HDAD, a new approach to audio atomic decomposition with hyperdimensional computing. So the goal of our research is to approach audio atomic decomposition at the symbolic level of atom parameters using something called hyperdimensional computing, or HDC, which is a non-traditional computing paradigm. And in particular, we're looking to encode long-duration atoms, which have many parameters. So as a preview, HDC becomes an alternative way to encode waveforms. So atomic decomposition is a tool for analysis, synthesis, coding, and transformation. And the atomic decomposition of a signal Y assumes a linear relationship between a redundant dictionary of atoms, phi, and the coefficient vector x describes the contribution of each atom in the dictionary to the signal. And epsilon is the noise and error term. So our idea is to encode these atoms into a vector of a different kind using hyperdimensional computing. And then, given this encoding, to extract the parameters from the encoding rather than from the waveform itself. So I'm going to start by giving some details on audio atomic decomposition, then some details on HDC, and bring them together for our idea of hyperdimensional atomic decomposition, or HDAD, and show some results. So atomic decomposition of audio starts with a parameterized atom prototype, where the atom is controlled by a vector of Q parameters. And a very common structure for this prototype is a windowed exponential. And in particular, the window typically controls features in the audio. And when those features are in the signal you're trying to decompose, you can describe the signal with only a few atoms, in which case the decomposition is sparse. And another way to put that is that X has only a few non-zero entries. And this envelope can typically be divided into two categories, symmetric and asymmetric. So very common shapes of symmetric atoms rely on a Gabor window in some instances, which is of infinite duration. And in many others, other finite symmetric windows, such as a hand window shown below, or a Blackman-Harris. And then the family of asymmetric atoms typically includes the damped sine wave, the gamma tone, formant wave function, and the ramped exponentially damped sinusoid, which is shown there below. So for many of our experiments, given that instrumental sounds are the combination of asymmetric signals, we choose to use the REDS prototype, given that it was designed specifically for audio. And in particular, the REDS gives a precise control over the attack and decay characteristics of the atom through its parameters beta and alpha. So, given a prototype, you have to select the atom parameters, and typically this is done by computing many waveform correlations, such as in an algorithm like matching pursuit. And when these prototypes are simple and symmetric, then these correlations can rely on fast algorithms to be computed, such as the fast Fourier transform. However, when the dictionary is populated with very long atoms, typically which are of asymmetric shape, storing this dictionary starts to require a lot of memory. Okay, so that's some details on atomic decomposition. And now to give an overview of HDC. So hyperdimensional computing, or HDC, refers to a set of models which encode data using high-dimensional vectors or hypervectors. And this can be conceptualized by a map mu, which maps some value r into this hyperdimensional space, which has size nhd, and it's typically between 10 to the 3 and 10 to the 4. And a very interesting property about these HD encodings is that the value being encoded is encoded equally at each position of the hypervector, in which case it becomes a distributed representation. So the particular HDC model that we choose for our project is called a vector function architecture, or VFA. And in order to arrive at the VFA, you start with a vector symbolic architecture, which pairs the HD space with a set of algebraic operations which describe how to build data structures. And typically in a VSA model, the relationships in HD space are categorized as either being the same or different. Then, using a property called locality preserving encoding, or LPE, this relationship can be expanded so that the relationship between encodings in HD space actually reflects the relationship of the values themselves. So that is preserved. And in particular, when that relationship is systematically defined by a similarity kernel, what is born is a KLPE, or kernel locality preserving encoding. So the vector function architecture arises when you take a VSA model, which uses a KLPE, and it's the model we choose for our project. So in order to actually build data structures in HD space, there are two operations which do this. The first is called the binding operation, and it's what we use to associate together parameters which belong to the same atom. And this is written generically as a circle. So we write binding two hypervectors u and v, u circle v. And then in the paper, we give specific common choices for binding, such as the Hadamard product or circular convolution. And then the other operation is the superposition operation, which we use to bundle atoms together, bundle atom encodings together to encode the signal. And it's written with just a plus sign. And it is done by the element-wise sum between the elements of the two hypervectors. So in terms of encoding particular values into HD space, this is done using a base or a root hypervector. And encoding encoding starts with self-binding, where we start by encoding some integer k by binding a hypervector u with itself k times. Then using an idea called fractional power encoding, this is generalized to real numbers, where we bind a hypervector to itself a fractional number of times. And for the Hadamard binding operation, this means simply exponentiating the elements of the vector by the value being encoded. And in the case of circular convolution, given the relationship of the Fourier transform, it becomes the inverse Fourier transform of the Fourier transform of the hypervector exponentiated to the value you're encoding. So details in the paper. And an interesting note is that these base and root hypervectors are actually generated from randomness. So that's how to encode objects in HD space. And then in order to decode them, the dot product is used to compare some query hypervector to a set of known hypervectors with decodings in order to return the encoded values. And interestingly, when we look at the if we look at the consequences of the binding operation in HD space, using the dot product to measure that, what the binding does is it destroys the similarity in HD space. So if you take two hypervectors and you bind them in HD space and you compare that to either of the original vectors, it has a dot product of almost 0. And the opposite is true for superposition, where the relationship, where the dot product between the sum is very high when compared to either of the constituents. So that's sum on HDC, and now to bring those together for hyperdimensional atomic decomposition, we start with an atom prototype, and then for each of the parameters in the prototype, we generate a base hypervector with which to encode the values. So given some signal y, which has this atomic decomposition, for each particular parameter, we encode it using the corresponding base hypervector using the fractional power encoding. And we also do this for the atom's complex gain. Then, in order to generate the encoding for a particular atom, we bind together all of the encoded parameters of that atom. And finally, to generate the encoding for the signal, we superpose all the atoms together to result in an HDC encoding of the signal, which we denote Z. So another way to visualize this process is, again, for some signal y, whose atomic decomposition can be visualized in this matrix of parameters. We start by first encoding all the values we want to encode. So as you can see here, the values are still oriented the way they were in the original parameter matrix, except we've introduced this axis of redundancy in the encoding, which is kind of projected backwards. And we do this for both the atom parameters and for the complex gain. Then, in order to encode the atoms, we bind along the parameter axis to bind together those parameters to encode the atoms, which allows us to collapse that dimension. And then finally, in order to encode the signal, we superpose along the atom dimension of the atom encodings, which allows us to collapse that axis to give us the resulting HDC encoding of the signal y, which, as we can see, is of fixed size NHD. And kind of interestingly, if we go back to what we started with and where we ended up with, as we can see, depending on what prototype you choose, it has a different number of atoms, and depending on the signal, it could have a different, depending on the prototype, it could have a different number of parameters, and depending on the signal, it could have a different number of atoms. But in either case, the encoding has the same size. So given this signal encoding, the problem then becomes generating the encoding Z given some signal. So you need an encoder. For our experiments, we choose a deep neural network encoder, which we feed tiles of a dual resolution short-time Fourier transform, tiles, and then the output of the network is this HDC encoding Z. And we train the network using mean squared error. So an overview of what the process looks like. We start with some parameter structure. From that, we synthesize a time signal, which we compute this dual resolution STFT with. Then we subsample it and give it to the network. And the network's output should be the encoding. And since we know the parameters, we can encode the ground truth hypervector and backpropagate. And then in testing, when we don't have this parameter matrix and we're giving it some unknown signal, we just decode the output of the network and resynthesize the signal from those parameters. So again, this overview, in training, we have synthetic signals, which are built from analytic expression of atom prototypes. We choose circular convolution to be our binding operation, a hypervector size of 1,000, 16 kilohertz audio, and a few different atoms. In order to listen to some of this, here we give the network a 6-second signal, and it returns to us some reds parameters. So that is the input to the network, and the network identifies 7 reds atoms in 2.3 seconds. Okay, and then, to also demonstrate the ability for the technique to decompose using atoms of many different parameters, we introduce 2 additional parameters to the reds, the frequency modulation rate and amplitude, and we give it this signal on the left. And it gives us back the parameters for which we build this signal on the right. So the network found 11 atoms in 4.4 seconds for an 8-second signal. And then finally, to show the ability for the network to give us parameters that we can coherently manipulate, also demonstrating another use of atomic decomposition, we start with this signal on the left. I just play an abbreviation because it's repetitive. Okay, so that's the reconstruction. There's also some sort of envelope, so the first one seems to be getting cut off, or I can't hear it back here. And then we can transform the signal by frequency shifting it down and decreasing the damping. And then we can do this further with this signal on the right. Okay, so that's HD-AD. What we do is we systematically build an encoding for atoms in HD space to be used in atomic decomposition of audio. We estimate the atom parameters and the gain in HD space, so we avoid waveform correlations. And this method allowed us to quickly decompose signals into long atoms with many parameters, which is sometimes a difficult situation when computing with waveforms. So future directions we see this going in, you can introduce other parameters to the prototype, such as chirp behavior or harmonics. You can use different features to extract the parameters from, and if you're subsampling, you can do some sort of time-frequency energy detection or some more creative time-frequency representations, such as a non-stationary Gabor frame, as well as choosing a different encoder in general. It doesn't have to be a neural network, although a long short-term memory, which would have some sort of fixed size as well, or just some sort of DSP encoder. It doesn't have to be machine learning. So anyway, we want to thank the reviewers for their helpful feedback, Compute Canada for the resources, and NSERC for some research funding. So if you have any questions, I'm happy to take them. So thank you.
I think it was on slide 12 that I didn't understand anything. It was something like the symbols are distributed equally in the space. I didn't understand what was meant with that sentence.
Oh, sorry, there's a typo, or?
No,
Oh, sorry.
I just don't understand what you mean with that.
Okay, good question. So I'll go the other direction now. This was a bad idea. Okay, so interestingly, one way to think of a time signal is as a high-dimensional encoding of atom parameters, right? It defines a shape, but it encodes it in not a distributive way. So for example, take the time parameter, and what you do to encode time in a time signal is you shift the shape to the position you want to encode it at. So, the encoding is concentrated under the window, and outside of the window, it's not there. So HDC kind of works in this almost orthogonal direction, where instead of just encoding under some envelope, you're more or less just rotating the position of these base hypervectors by the value that you want to encode, and you're doing that at every single position. So in that way, it's distributed across the whole vector instead of, for example, waveform, which is just under the envelope. Does that make sense?
A little bit different. Probably if I think more about it, but yeah, thank you.
Okay. Well, I'm happy to talk after, by the way.
Thank you. Might be a simple question. So, first of all, is there any dictionary learning? So, is this a fixed set of dictionaries? It's just massive, or are you adjusting parameters in the dictionary?
So, if by dictionary learning, do you mean like learning the waveforms themselves?
Yeah, or adjusting the atoms during the encoding. During the process, let's say.
Yeah, so there's no shaping of the elementary waveforms. We decide that by choosing a prototype. so reds for a lot of the examples. And then we train the network to return specific encoding, specific values for reds parameters.
So is this essentially a fast computational shortcut for a matching pursuit? It's just that you have a massive dictionary, and doing a matching pursuit would be very inefficient. And that's a faster way, but it's essentially doing the same thing. Am I kind of on the right track?
You're on the right track, and which is why I prepared this slide, actually. So, interestingly, because of kind of what I was showing earlier, where you start with some signal, which has atoms stacked on top of it, and then you end up with another signal which also has atoms stacked on top of it, they end up looking very similar, and you can actually do a very similar process in order to decode the atoms. So here is a bunch of symbols, but basically what it means is that many of the steps that go into some matching pursuit that you do with waveforms, you can also do with this HDC encoding. The advantage being that they're much, much smaller. So instead of having some 2-second atom sampled at 16 kilohertz, you have a vector of 1,000 samples. So that's a lot smaller.
Cool, thanks.
Yeah. And there's also some stuff about a considerate, but we can, yeah.
So would it be fair to say that the trade-off is high dimensionality of the encoding to time, like the length of the vector? You augment the dimensionality to capture longer. Am I?
Yeah. So it would actually not necessarily time, but sparsity.
Okay.
So I guess the more atoms you jam into some encoding of a certain size, the noisier your parameter approximations are, but that can be accommodated for by making the space bigger. So it scales more with sparsity than it does length and time, which, given the assumption of a sparse decomposition, should be fine, right? As long as you tune it, yeah.
Thanks.
Hi. Maybe it's not going to be as smart a question as all the others, but
That's
is
fine.
this in any way similar as the wavelet encoding in images? Because it kind of feels similar to have a library of something and then match those snapshots to whatever you want to encode. Am I getting the basic principle right?
Yeah, in terms of atomic decomposition in general, yes. Like, so in the beginning when I mentioned like the symmetric shapes, which can rely on a fast Fourier transform, like a typical short-time Fourier transform is an atomic decomposition where the atoms are windowed sinusoids by a hand window or whatever. And then I'm not too... Philippe would know better about the wavelet case, but yes, the mother wavelet or in its translations correspond to atoms, or?
We could have used the wavelet atoms, and it's an atomic decomposition. Then the parameters would be frequency, scaling, and possibly others. But in this context, all was starting from the idea that we want basically this refined time sine wave, because that's what we have in many sounds. Yeah. But it could be any, it can start from any set of atoms. Yeah. Mm-hmm.
Thank you.
Thank you.
Hi. So if I got that correctly, the neural network that you use as an encoder tries to map different atoms, or does try to map the signal to different atom components, kind of, and parameterizes the atoms, right?
Mm-hmm.
Now I try to think back of what I wanted to ask. So, sorry, I actually lost track.
Okay, if you remember, just let me know.
Maybe I will just go back to you after the presentation when I
Absolutely.
remember my question. Yeah.
Absolutely, yeah. It's been a...
At least you answered one part of the question
Okay,
already.
good.
Yeah.
At least one.
Yeah.
Thanks. So I think it's time to end the session. And so thanks, Christian, and thanks to you all.